So I had a 4-page entropy inequality. Some of the terms had to be identically 0, and that gave me some results which I already showed you, like stress is only either pressure or sort of interfacial tension, and that leaves me with 2 pages that are not 0, but then I define equilibrium, and then under equilibrium they are 0, and I define equilibrium when there are no velocity differences in the system. I always emphasize this because there could be velocity. It's not that there shouldn't be. Actually, there is a velocity. Everything is moving with the Earth. So it is moving. It's just that the phases don't have, or there's no velocity differences in the system. There's no temperature differences, no temperature gradient, and then the rate of changes of saturation are 0, and there are no exchange of mass or energy. And with this as my equilibrium restrictions, entropy inequality, entropy production becomes absolute minimum. Therefore, its derivative with those equilibrium variable must be 0. That gives me additional equalities. One of them is that the pressure of solid must be equal to the weighted sum of the 2 pressures. The pressure difference between the 2 fluids is related to what I identified as capillary pressure, which was basically change of free energy of interfaces with the change of their area, and that I find this momentum exchange between phases and interfaces has these equilibrium values. I also find that there can be no heat flux, there can be no heat exchange, and the Gibbs free energy of all the phases and interfaces must be equal per mass, must be equal. So if I now take some of these and put them on my balance laws, for example, take momentum balance equation for a phase, and I substitute the fact that I got this equilibrium, they were equilibrium parts of the exchange of momentum with the neighboring interfaces, and this is the equilibrium part. Then there is a non-equilibrium part, which is function of all the independent variables. And if I neglect the inertial terms and I substitute this there, I also, for a stress tensor, I substitute its pressure. So I put that pressure for a stress tensor. These are these parts from T hat, and then the gravity. I get these. Now you can see that these, some of them will cancel. I only get epsilon S del P here out of it remaining. And I can assume a linear relationship for this non-equilibrium momentum exchange, this friction force. In terms of the velocities, oh, yeah, here it is. If I do that, I put it in there. So if I assume this tau hat to be a function of V alpha S. Remember, there are other parameters here, variables. For example, there is also V beta S. So I could potentially assume that tau hat alpha to be a function of V beta S as well, the velocity of the other phase. And if I don't do that for now, I get Darcy's law, where the V alpha S is a linear function of, now on the right hand side, whatever it was. And I see that I get the usual term, but I have this extra term in here, that the free energy of the fluid can change as a result of change of saturation. And what is interesting is that if I remember, the Gibbs free energy is defined this way, And then I realized I can go through it and I can show you. If I take the gradient of this, I don't know whether I'm going to do that. The gradient of Gibbs free energy, therefore, is gradient of A, but the gradient of A is dA d rho del rho plus dA d theta and then plus dA ds, sorry, del S. Now, if you recall, the AD rho is P over rho square. And del, was it? So, because I can get del P out of this, I forgot how it was done. Please forgive me. But I can show that the sum of all these two terms is equivalent to the gradient of Gibbs free energy. I'll do that in a minute, okay? Because del P itself is, I can't remember how I did that. Oh no, sorry, here, I also have to add this. Yeah, if I add this, then the rho cancels, I get del P. Yeah, so add that, this is correct. And then, so that's P over rho, but here from del of this, I get the 1 over rho del P, and then minus 1 over rho square P over it del rho. This cancels this, and I get del P. So I get this term plus this term is rho del G. I put that in here, so that's my.
So does this now take temperature gradients into account?
Oh, sorry, I should also add the temperature gradient. I wanted to replace it. So there is indeed a term from the temperature gradient in here. So I think it's a minus dA d theta, which is S times temperature gradient. So potentially you can have that. And as I said, if you had assumed the non-equilibrium part, tau hat, to depend on other velocities, I will have here actually a coupling term. Some of you may have seen Darcy's law for two-phase flow. They say that the velocity is related to the pressure gradient of phase, but also a coefficient times the pressure gradient of the other phase. They call it a coupling term. We can get that as well. We can also get, sorry, should I go back?
No, I'm just commenting sideways here, but I should say it to you too, that this will mean that the K coefficient will be the same for all contributions to the gradient in G, meaning that the temperature gradient will have the same coefficient in front per unit of driving force, so to say, as the other contributions to the chemical potential or the Gibbs energy.
Well,
and this is not observed experimentally in single fluid systems.
Well, I must go back. I said that this T hat is a function of all the independent variables. And I chose to write it as a linear function of this only for the sake of getting Darcy's law. It's also a linear function of del P, del theta. If you put that there, you get an extra term related to del theta with its own coefficient.
Oh, okay.
Tau hat is a function of all the terms.
That's
so it's a function of.
Want to compare.
Correct. Okay. So you can expand it in terms of all those independent variables which were gradients. You can also write it to be related to the deformation tensor of the solid. But then it will have a third rank tensor multiplying, which we say, okay, that is not allowed. So it could be a function of that as well. But the coefficient that I put in here, for example, that K, is still a function of porosity, is a function of deformation of the solid, so this can change if the solid is deformed. So it's still not a constant. It's just not a function of the velocity. That's the idea. It's an independent function of the velocity and the temperature gradient if you expand it as well. Okay. Now we can look at the momentum balance for solid, for example. And then put in the equations we got for a stress tensor. There was a solid pressure, and then it was equal to this gas is the non-wetting phase. These terms, but it was only at equilibrium equal to this. So potentially it has an extra term that is related to differences between them. And there is an effective stress tensor. And yeah, so this is then what you will have for the total stress tensor of the whole medium when you add the fluids and solids together. What else do I have here? So let's look at this. This is, I'm sorry, this is porosity and saturation. So I copied this from some other presentation. So this is Pn. And it is saying that this is Pc, is really related to the rate of change of saturation of the whole system, if rate of change of energy of the whole system as a result of change in saturation. And under non-equilibrium conditions, because this must be not larger than 0, then this is still a function of all the unknowns. If I make a linear approximation for this and a linear approximation for the porosity change, I get this kind of equations. Is that already said? Yeah. So the stress tensor in the system can have the regular terms, which are effective stress of the solid, the sum of pressure of the fluid, but it can also have a non-equilibrium term related to the porosity change. And the Pn minus P double is equal to Pc, but then potentially has this non-equilibrium term. Here is a linear approximation. Doesn't have to be linear, but yeah, we work with linear usually. Now, I must say, so as I said, we did this work back in '89, we published in '90, and I had no idea what this was. I must say I didn't believe it at all. I said, yeah, Pn minus Pw must be equal to Pc. What is this? I had absolutely no idea. And I gave a presentation in Holland, and there was this soil physicist from US, John Niebuhr, visiting Wageningen, the agricultural university. And he was in the audience, and after that, he came to me and said, yeah, this has been measured in soil physics in 1960s, in 1970s. And I say, well, how did they measure that? They say, well, he said they did experiments where they measured what they call soil water characteristic curve, or water retention curve, PCS curve. They measured PCS curve the way they always measure it, slowly, for a week it takes to get the curve. But then they also had measurement. They said we drained the system in half an hour, in 1 hour. And they had tensiometers measuring, and they got a totally different curve. And the difference was depending on how fast they were doing it. And this must be this term here. So I went to the literature, yeah, there was lots of them. And even from the published data, I could already calculate tau value, because they had this PC for a static situation. Then they had, okay, we drained the whole sample in 90 minutes. So I knew in 90 minutes saturation went from full to some value they gave. So I had this, I could calculate tau. easily. So this is one example of really deriving something that you had no idea it means really has some physical value, and it's been indeed observed in practice. But of course, it's not just a matter of, I don't think I showed you that. Maybe next week we can talk about it. What are the practical consequences of some of these results that we had here? So for example, one of the results is that when I define capillary pressure to be the change of free energy of phases with saturation, then here, the saturation, that means capillary pressure is a function of densities, temperatures, the saturation, but also interfacial area. And this is a different animal than what we identified as a capillary pressure in our study, or is it? So that's, you can make link with the current. I think I finished my slides for today. So lucky you can. But maybe we can have a short discussion, or
can I still have one more question about
sure.
the last term? So I can imagine that if you talk about the people who did soil science and were looking at draining a sample, that actually then the saturation changes because of flow. I mean, things flow in or things flow out. But I can imagine that there might be, for instance, condensation, evaporation. Would you then get the same coefficient in front of the S dot?
What do you mean by condensation? I mean, you mean when they are doing long-term measurements?
If you know, even if supposing you have a soil sample and you just increase the water vapor pressure and see how it changes the saturation because it starts to condense, then as you have an S dot, is that the same S dot that you would get if you actually pump in water into the...
Oh, I see. So I think if you do what you suggested, happens slowly, I assume it doesn't.
No, but if it happens slowly, you don't see anything, right? Then you get capillary pressure, I guess.
Exactly. So if it happens slowly, there is an S dot, but it's negligible.
No, but I mean, but suppose it's not negligible. I mean,
yeah, then I guess it would be the same thing, because by condensating water, you increase the water pressure, and if you do this fast,
yeah,
then the capillary pressure hasn't, the interfaces haven't adapted to this new amount of water, that saturation that's there. So it takes time for it to equilibrate. If it is fast, if it is slow, it will equilibrate, of course. But the whole idea is that you have a soil sample, it has a saturation, it has a water pressure, it has an air pressure, and it has a PC that corresponds to that saturation. Now, somehow you change the water pressure enormously. Nothing has changed yet.
yeah.
Saturation hasn't changed yet, so why would PC change? PC hasn't changed, but you change water pressure. So this equality doesn't hold anymore at that moment. Equality has to be restored by water leaving the sample, and therefore, entering the sample, the PC going down. Okay, then we go back to this equality. But that takes time. In the meantime, this term then is playing a role.
But you could imagine another constitutive equation describing exactly that change that you are after, because if you introduce water suddenly, you will have a gradient in saturation. So, and if the two processes are coupled, you will have the impact on the PC or the other term via another rate equation. So you don't necessarily have to add this tau S dot, I feel. So
Right.
there could be other options of doing it.
That's absolutely correct. Look, this S dot is a function of, sorry, let me look at back this. I have my entropy inequality. This is what I call the residual entropy inequality. The terms that are there are not identically zero. They could be zero under certain conditions. Okay. Then I say, I make these that are in the bracket a function of these that are say forces. And in this formulation, I assume this to be only a function of that. I could have assumed, because I also have q del, see, these are dots here, I have q dot del theta as one of my terms. I have a lot of other terms.
Yes.
I could say this is a function of s dot and n dot and del q, del theta, and velocities, because they're also there. Maybe I should, you see the 2-page remaining entropy inequality.
Yeah.
So potentially this could be a function of all of them.
So in that sense, it is some degree of freedom here in
It's
in
an
setup.
approximation,
Yeah.
absolutely.
While we are guided by the Onsal relations on how to do the obey the symmetry, so to say, of the system.
But Onsager relation doesn't say this difference cannot depend on, say, all the other gradient of porosity or gradient of saturation. It only says that if you have a set of fluxes and the driving forces, then there is a symmetry in the coefficients.
Yes.
But what the
And then you
relations
have the-
should be, there are many
Yeah,
possibilities.
but you have also, like we commented before, you also have the Curie principle and the observer invariance and things like that.
Yeah, I mean, this definitely is possible to have many other driving forces. It's not excluded. It's not unique results. It's only one simplified relationship, which I must say, I was guided by seeing the data.
Data.
In fact, that's another interesting point. We don't need all this approach to develop this equation. There was a guy, I found out later, Stauffer, in Switzerland in 1978. He also did measurements, slow measurement of capillary pressure saturation curve, fast measurements, and then based on that, he proposed this equation. Exactly this equation. So yeah, you don't need all of this, really. But this is a way for
Very
ignorant people
important
to...
and central equation, yes.
Yes.
I have to ask a little bit more general question. Okay, so you are now at the continuum level, and you go in and measure the pressure at some point. And that point is not really a point, but it's so wide that it still continues. But you get one number out. How do you know this is with Pn or Pw?
Well, once again, what do you want to do with it? I want to put it in my momentum balance equation and solve problems.
No, but then it contains variables that are not measurable, because you cannot make any difference between Pn and Pw.
Oh yeah, no, that's a matter of measurement equipment. I have measurements that measure
At the
Pn.
pore level, yes, but at
No, at average value.
How? But I mean, how do you say that this is Pn or Pw? How? I mean, I go in measure now at the point. What pressure is that?
Yeah, look, every single measurement you make, there are issues with it.
No, but I mean, the issue
So
is more.
you measure temperature, you measure concentration. There are always issues. Okay, what are you sampling? But we have transducers that at the opening of the transducer we put a membrane, and the membrane is extremely hydrophobic. So that means when the oil and water comes along, if oil is the only liquid there, okay, then the oil is there. As soon as a drop of water comes, covers the membrane surface. And from now on, I'm measuring, hydrophobic, yeah. So, go back. Extremely hydrophobic. So, if there is water, is the only liquid there, it measures water pressure. But as soon as a drop of oil comes, covers that membrane.
Yeah.
From now on, I'm measuring oil pressure.
I know that people did that here. Although Thorseth told me that he tried to do exactly these kind of experiments and they really didn't work. It gave no good answers at all.
I don't know what
I don't know. I mean,
was meant by good answer, but we're really happy with these measurements. I can show you results that we have two transducers, one of them oil, one of them water, and they are both measuring the same pressure when the water is there. And the oil comes along, the water pressure transducer changes a little bit, the oil pressure transducer jumps up because oil pressure is much larger than water pressure. It was drainage. So, yeah.
But of course, the question is...
only measure the pressures outside the porous medium.
No. This is in contact
Yeah.
with this.
But then you are basically assuming that because what you have in your equations is of course the average pressure over a volume.
No. Pressure is not a volumetric quantity.
Well,
Pressure is a surface quantity.
it's a pressure. Well, the pressure is in your equation as I have understood it. It's basically so I have I take the pressure, the local pressure somewhere, and how that pressure is it may vary in your volume, and then the macroscopic pressure is the average of that. Isn't that how you define it?
That's not how I define pressure. I did not. I fully understand your question, and I disagree with people who define pressure at the porous scale, and then they say macro scale pressure is the volumetric average of that porous scale.
Yeah, so
as an approximation,
so
it's fine.
The first day. So how did you define your pressure then? Is it the
I didn't-
derivative of something?
The pressure was the stress tensor under equilibrium conditions. That's how it was identified as pressure. I didn't define pressure. There was no pressure in my equations. If you look at the balance law, there is no pressure. I start with the entropy recall. There is no pressure there. At some point, I get this combination, and it is out of, it's not by choice. Okay, I think it's here. I'm sorry.
Yeah, so it's a macroscopic. And that's not
Yeah.
what is transducer measuring.
Here I got a term which was dAd rho times rho squared.
Exactly, which is a macroscopic quantity in a large volume, right?
Yeah.
But what you're measuring with your transducer is something local.
It's not local, it's over many pores.
Yeah, but
It's not volumetric, you're
yes,
saying.
but the situation where you measure it.
It's a surface property.
Yes, but the situation where you measure it is it's extremely changed from what's inside your bulk. You have that membrane.
Oh,
Okay? So actually there you are measuring a local pressure, a pore pressure.
It's not measuring pore
So
pressure.
is that
It's
the same
an
as this one? This is the
average,
question.
average over many pores. Why is that?
Yes, but it's in a situation that is totally different from what is in the bulk, isn't it?
But when you measure temperature, are you measuring volumetric temperature? You put a sensor there. The sensor has a surface. The temperature is the surface of that sensor is measured. Is that the temperature?
Yeah, this would be correct if you didn't have P alpha. If you had P, you have something you call P. That might be exactly what you are measuring, or even there that I would have some problems with. But that would be P, wouldn't it be?
No.
So I want to measure something over all pores. You must agree that the macroscopic situation close to your membrane is different from what is in the bulk, and it is the bulk situation you want to measure.
Take momentum balance equation. There is a divergence of stress tensor and divergence of pressure. I take my volume, I integrate that momentum balance, and it's a simple balance. It's del P minus rho G, porous scale. You can also write it as the macro scale. If you integrate over your volume that you are interested in,
But you're not integrating over volume, you're integrating over surface, huh?
I have that momentum balance. What do you do when you solve a flow problem? You solve momentum balance equation. I'm interested to know what is it I should put in my momentum balance. I'm not interested in pressure. I'm interested in what is it when you solve any flow equation, you solve Navier-Stokes equation. Okay, when you solve Navier-Stokes equation, it's a momentum balance equation. It has a del P in there. Please let me finish this. You integrate that del P over a volume, you see that pressure becomes a surface term. It's P times area.
Yes.
So that's what I should measure.
Yes. Yes.
So
yes.
I have absolutely no problem, either in a porous medium or in a tube, to measure pressure at a surface and then at a boundary.
And I totally agree with you. Okay?
Then I am making the assumption that in a one-dimensional flow, that the pressure I'm measuring at this point at the surface is the same pressure everywhere, because laterally I have no macroscopic flow. So I assume that when I do a column experiment and I measure pressure at the
But you have
side,
a gradient. You have all.
not laterally. No.
Yes, you introduce
Not
you introduce that gradient by the membrane. It introduces that gradient laterally. At least one
Okay,
might
look, there
worry
are,
about that.
Can we separate the question in two parts? Part one, let's assume I have an ideal measurement instrument that you will be happy with, and I measure pressure at the side. Is this pressure what I should measure and put in my momentum balance equation? I say yes, because I need for my momentum balance equation a surface force. A stress tensor is a surface, is not a volumetric, and that's what I should measure. Is my transducer a perfect measurement instrument? Yeah. I don't know any perfect measurement instrument of anything. Measure temperature.
Yeah, but what we are, I think we're trying to say is that you are measuring your pressure, but is that pressure P alpha? Is that constant?
Laterally it is. If
Laterally.
it is one-dimensional flow,
Why?
macroscopically.
Why?
Because the
Why?
sides are closed. I read your paper yesterday. You say the sides are closed, therefore there is no macroscopic flow laterally. If there is no macroscopic flow
So
laterally,
where is this in your equations that P alpha and P beta should be constant?
they shouldn't be in general constant. In one-dimensional,
In the one-dimensional flow. Where is that in your equations?
it's not. It's my boundary conditions tell me.
Yeah, but how do you know that?
Yeah,
Okay, so
I don't see
and-
this, I'm
and
sorry.
okay, so water goes through it and oil does not. How do you know that that difference you measure is not
It's a
just that you
combination
have
of those two
different
elements.
contact area? Simply because oil doesn't.
Once
penetrate, so it
again,
blocks the
I am
direction.
not
So-
invoking that the transducer that I'm using is the best transducer in the world. And I'm not saying that there is no transducer, or for that matter, any measuring instrument without artifact. But I really don't get your point, because even if you define average pressure, macroscopic pressure, as the volumetric average of pore pressures, okay, but why is that better?
No, I'm not saying that all actually, I don't disagree with your equations or anything. I'm just saying, are these measurements, are they really measuring what you are
That's a
explaining?
very valid question.
And
yeah,
I don't,
yeah.
I'm
But
not really convinced of that.
No, I can fully understand. But in terms of what I should ideally measure, I should ideally measure pressure as a surface property. And then If I measure it at the side, is it the same inside? Well, depends on the system. It's two-dimensional, three-dimensional. I don't know.
To verify something, when you say that the P alpha is constant, is that in the direction of the flow or in the direction normal?
No,
to
no,
the flow?
normal to the flow.
Exactly, that's a very important distinction. And I think that is what maybe is confusing.
No, I'm saying that the equations, I believe, give a restriction on the combination of the P alpha and the P beta in that direction, and not on each of them separately, because you will have a saturation gradient in that direction actually.
That's what I don't understand.
You
Why
impose that
in one-dimensional flow, why do I have a saturation gradient laterally?
Because you impose that by your transducers impose that.
Because they are wetting.
But look,
hydrophobic,
look,
hydrophilic.
so you mean at the membrane there is difference in pressure gradient, not through the column?
Yes, through the column because of the membrane.
Yeah, okay. I show you simulations we did. Porous scale, we included the membrane and the housing behind the membrane of the transducer. We simulated all of that because you're absolutely right. For the measurement to occur, there must be a little bit of fluid exchange between the pores and the housing behind the membrane, because behind there's a membrane, there is a housing, and there is a electrically sensitive little plate. And these are absolutely negligible, but at least according to the simulations, because we cannot do measurements, of course. So I don't think that is really of any major significance, if I understand what you're referring to. The fact that a transducer across the membrane, you have a pressure difference, or actually if there is no flow, there is no pressure difference, but there is a tiny
This
flow.
was not what I was referring to. Basically what I'm referring to is that you have a boundary condition in parts of your model where the saturation is 1. And that has to, by capillary forces basically, this does not die out immediately. It has to be.
You mean saturation inside the transducer?
It
That's exactly what I'm saying.
Not inside the
We
transducer,
simulated
but
that.
inside the porous medium.
But why inside the porous medium saturation is 1? Oh yeah, it's covering the.
Yeah, you have.
Okay, now you are saying that one single pore location dominates everything.
No, but it's not one single pore. It's exactly what you're saying. It's
I mean one single.
Pores. In all those pores.
In the lateral direction is
in
one
all
pore.
those pores, it's 1. Okay, and that has to translate. It doesn't die out immediately.
All right, I don't know. I mean, you should convince me that really is such a significant effect. I don't know.
It must be.
Laterally, there would be flow. So there is never a one-dimensional flow macroscopically if you put a transducer.
Yeah, that's what one's trying to say.
All right. I would say then we should throw away all the measurements, all the even numerical simulations that people have.
Not necessarily.
Okay, but if it is significant. I'm sorry, was there another? Okay, then maybe we stop, but I'll be very much interested to talk to you and show you some of these simulations we did.
Yeah,
We really simulated the whole transducer as part of the domain.
And
Okay.